Yes, so this is about a recent paper we've done, and I will tell you about this. But first, given this is a mixed community, very quickly, the Higgs boson, what it is. So the Higgs boson is a key. Je sens de l'écho. Oui, merci. Non, voilà, là ça va, oui. So the Higgs boson is really the key of the standard model. It's the particle which is responsible to give the mass to the other particles. So we have discovered it. You were still there, Jean-Baptiste? Yeah. 2013. It is some time ago, but we are still studying it. And why do we study it? For many reasons. But one, for example, will there be a tomorrow? There is this paper in Pour la Science, which is normally a serious scientific magazine in France, and the title, which is usually not clickbait, but it is clickbait. Vacuum decay, a threat for the universe. And what could happen? What is about? What could happen? It is started 2012. So the Higgs, the field Higgs is what created the mass of the particles, and it turns out that the Higgs field might be unstable. And this diagram is a calculation of the stability, and we see that it is with two parameters like the top mass and the Higgs mass. We see that we are really at the edge of we are even metastable. It means that somewhere in the universe, it means that somewhere in the universe, maybe there will be a phase transition which will propagate to us at the speed of light, and we will never realize. Okay, but of course it's really a fundamental parameter. And so now on this measurement, so this is a specific measurement of the cross section, of resonance cross section, I should have said, where there are two Feynman diagrams, the one which is Higgs to 2z and then to 4 leptons, and this one would glue to z and 4 leptons, and we see that the two diagrams have the same initial state and the same final state, and they interfere, and not only they interfere almost maximally negatively. So it's really in a situation of the well-known Young slit experiment, where you have the two slits, and then the two waves are interfering on the screen. And here the whole of the two slits is a diagram, the gluon diagram, and the other one is the Higgs diagram, and we want to measure the Higgs diagram. So basically we are measuring the results of the experiment and try to measure the size of the slit as a function from the experiment. Okay, so we have two Feynman diagram interfering. So it's the amplitude which are calculated. So we need the square of the amplitude, which gives probability to have an event. And by some conversion, we scale the signal which we are looking for, the Higgs, by the square root of mu. And then this is the formula where we have two terms, and then an interference term which turns out to be negative. And then this is the yield, so the number of events which we get when we collide a proton for some amount of time. And this has this formula here. And in practice, this is what we would see. So this is normalized as usual to the standard model. So what is the predicted value of the Higgs? So this is 1 by construction. And then if the signal was 0, we would have in fact more. And then if the signal increase, then instead of having more event of a given stuff at the beginning, we have less event of a given stuff, yes, and then decrease, and then it decreases again. So this is quite untypical, and as we will see, this is quite adapted to look for a new way of measuring the signal. So this is the goal of simulation-based inference. So before I mentioned the traditional, not traditional way, because traditional way, okay, since the beginning of the Higgs studies, we use machine learning. At the beginning, we use BDT, boosted decision tree, a lot. Nowadays, still BDT, but also neural network. But in most cases, what is done is to train a model to separate, to classify signal versus background, to put signal on the right, background on the left, and then we look at the data, and then the excess here of events, which are most signal-like, is evidence of the Higgs boson, and in practice the measurement of how many the cross section, so how many Higgs boson do we have? The measurement is done with a proper likelihood fit, proper bin likelihood fit on the first bin here, and this is done with a negative log likelihood with a sum on the bins of the expected the logarithm of the Poisson of the expected number of events. So nu is the number of expected events of a given type in a given bin. Voilà, this is the usual way to do this. Now what we are going to do is, instead of doing a bin fit, we're going to do a non-bin fit, where the unbin fit, sorry, unbin fit, where the likelihood, the product of event likelihood, so the log likelihood is the sum of the logarithm of the likelihood. And what we do is that we divide everything by reference probability, a reference data set, because it's easier to fit density ratio than to fit absolute density. Okay, so this is the formula. So this is the formula to have the likelihood of one event. Okay, and this is divided by the yield, which depends of mu, and then there is a sum of all possible processes, which gives me an event of characteristics x. X is what I can measure in an event. This is a vector of dimension. Right, at the beginning, it's a dimension a few millions, because we have a few millions sensors in the detector. But this is reduced to let's say a dozen parameters, which are the parameters which can be measured from the final states. And divided by Pref, we have now this formula for one event. The density ratio is the sum of a formula, which is the formula which I have computed before. I will show again, which depends of mu, and then density ratio, which are independent of mu. This is very important to have this density ratio independent of mu. This we will obtain from neural network. You could have, in principle, density ratio which depends of mu fitted with neural networks. It's called parameterized neural network. But as you will see, it's quite difficult to correctly fit a neural network density ratio, and to fit this with, in addition, the dependence with mu would be even more difficult. But this is a key point to have this density ratio here. And voila, a bit more detailed. So we have the different processes. So BS, let's start with S. S is the signal. It's a simulation of the signal data. B, the simulation of the background. And SBI, the simulation of signal plus background plus interference. Of course, interference being a depletion of event, you cannot have a data set with just the interference. It doesn't have any meaning. So one is able to build this data set, complete data set, by a combination of these three data sets, plus the last one, which is a non-interfering background, because there's always things happening which is not related to what you expect. So all the other backgrounds. So then you see the formula here, where there is a dependence with mu, square root of mu, and voila. So this is still the probability for one event. So how can we estimate the density ratio? This is relatively simple on theory. when does use a neural network, so we end up with a neural network which is qu'est-ce que j'ai fait? C'est tout noir là. Neural network, which is a dense neural network, but quite relatively heavy, with five layers of 1,000 nodes. And when such a neural network is trained with a binary cross entropy, then by definition, the score, what you get from neural network, is converging to the ratio of px over pref, when the neural network is a classifier between x and ref. And then it means that the density ratio is obtained by S divided by y minus S. So these are the features on the left. As I said, the 13 features which are deduced from the 4 momentum of the final particle in the final state. There are 4 leptons in the final state plus two jets, and there are different high-level variables which are computed from this. So the key thing, the real problem on which we, or rather the students, have spent literally months, is to have a proper calibrated, related to the first speaker, calibrated density ratio. So a neural, if a neural ratio gives me a probability, how can I be sure that it is really a probability and not just a variable? I like to make the example of any meteo applications which give you the probability of rain every day, and then at the end of the year you can check whether your application is correct by making a graph of the observed probability for rain with respect to the predicted one from the app. And you expect something which is on and diagonal. And if you don't, then you can think of recalibrating. Recalibrating means by doing a transformation of the horizontal axis, so that everything fits on a diagonal. But in practical, we've seen many practical difficulties with this post hoc calibration technique. And at the end, what we are doing is ensembling, which is that to compute 100 different neural networks on the same randomized dataset and take the average. And this works, but you will see that, but this is really very resource hungry, because you have to fit 100 neural networks, and there are many neural networks. Very important point that when doing this, why we have to do this assembling, why it cannot work just out of the box, is because in this case any overtraining is fatal. So when you do any kind of a learning curve, you always have these things that when you increase the model complexity or when you increase the number of iterations, etc., the validation error split from the training error. So the validation error is this one, and the training error always improve, and then at some point it splits. So when we do the usual thing with the classifier, we don't really care that we are obtaining density ratio. We only want to have some variable which is able to separate the signal from the background. So it's just a ranking variable to rank from the background-like event to the most signal-like event. We don't really care that the results are different. So we typically do this because we see we don't gain anything by adding more complexity. And then when we are here, it's optimal for a typical approach. We're doing a bin approach, but here clearly the results are different between the training and the validation. It means the density ratio will be wrong. Okay, but this is what we get. That's the density ratio, the score with respect to the Monte Carlo estimate, the measured one, and we see a perfect agreement. And of course, this was months of work to get this perfect agreement. However, this is not the full story. The fact that a particular point is on a diagonal here, it means that for the points where the value is, for example, 0.2, then in average it's well correlated. But it's not the full story, it's just a kind of projection on in the feature space, volume in the feature space. In average, the calibration is correct. The second check which we can do is, we didn't have a good name for that, is to do a reweighting. So we realize that once you have this density ratio, you can transform a dataset into another one. So since you have the px over pref, we can take the ref dataset, the blue one, and then for every event multiply, give it a weight which is px over pref, and then you have a new dataset which is reweighted, and which is the red one, which you can compare to the original X, and you can see it's, well, here it's a bit easier to see. It's a very well agreement. So with the density ratio, I can, with my reference sample, I can create any dataset for which I have this density ratio. And the fact that it agrees shows that, gives me confidence that everywhere in the feature space, density ratio is correct. You can have, and we see this, you can have this perfectly in a line, while some of these variables showing disagreement. The third check is to do the same kind of check, but instead of checking for the standard dataset with mu equals 1, since we are going to measure mu, we should check that this is still working even if the value of mu is different, and this is again working well. Before I move on, I need to introduce something which is used a lot in particle physics. It's called an Asimov dataset. It's because we don't, would like to have, we don't have the full PDF, multi-dimensional PDF on a full parameter space. This is, pardon? C'est les vues qui partent, c'est ça. Ouais. So we don't have the analytical PDF. We only have a simulator, which is very, very expensive, which can which can sample from this PDF. But then we want to have something which would be as handy as having a quick simulator. And so what we do is we build this Asimov dataset. So we generate events. Is very, very expensive, 10 to the 7 CPU hour typically, and we reweight these events such that any volume of the dataset, any small volume of the dataset, which you can describe in the way you want, the integral on this volume is the same as the sum of the events of the Asimov dataset in this volume. That's the definition of the Asimov dataset. And then the very nice thing about it, so it is very handy to have a sample of events for a specific experiment. And the second reason it's very handy is that it was demonstrated with a very, very famous paper in the community. It's one of the papers which is the most cited ever. That the log likelihood of the Asimov dataset is the expectation of the likelihood of the data if you were doing millions of experiments. So redoing the Laché runs, the data here is for Laché running for 3 years, and you have to have millions of years of Laché. Of course, it's impossible. One interesting thing, I will come back to it if I have time, is that some events have a negative weight. This is quite a pain, and but we have to deal with that. Okay. And then when we do the likelihood with the additional data set, we have these curve. So if any of you has used the likelihood in any tutorial, typically you have, if you do this with a simple linear regression, typically it looks like that, where you have a nice parabola, and then the minimum, of course, is the estimated value, and the width at 1 is divided by 2 is the uncertainty. But here you see it's not the same shape at all. It's not symmetric. At 0 it looks like it diverges. It cannot be less than 0, so there is asymmetry. And clearly it's the minimum is very flat. It's very flat. But still we see that the minimum is at 1, is what we expect. So that's good. It means that it's a consistency check which we like. I forgot to say that by definition the plot that we're going to show are always with respect to the minimum value. Okay, so by definition this curve touches the axis. Another check is that we can now mimic the fact that instead of having mu equals 1, so a standard model, we can have mu equals different value, and we check that we are able to, according to the injected value, we can recover the same value. They are all on the same diagonal, so that's good. But then since it's about uncertainties, we really want to be able to evaluate uncertainties. So normally the technique is simply to get measure the intersection of the curve with the 1 and 4, but this is in the limit of Wilks' theorem, and since we are in an uncharted territory, are we at the symptotic limit? So we need to check this, and this is again a few months of work. So first we want to do pseudo experiments. So pseudo experiments, what are they? We want to answer what happens if now I make a measurement, 3 years of data at the LHC, what am I going to have? And we know we are going to have about 2,000 events, okay, and sampled from this PDF, which I don't know, but which is emulated by the Asimov dataset with 10 million events. So I take these 2,000 events, I do the NLL, and I get one of this curve. And I do this again, I get another one of this curve, and here there are, I think, 50 different curves. And what you can immediately see is that they are quite diverse. Okay, so the red one is, reminder, the red one is the average. Okay, but then you have some which have a second minimum here. Okay, some like the one here has no minimum at all, but except close to 0, and some have a minimum but at a large value. So it's quite different. And now we want to do the Neyman construction. So we want to build the 1 sigma and the 2 sigma interval, and we do it experimentally by drawing many pseudo experiment, and then we look at the intersection of the NLL with the input value, which is 1. Okay, and this intersection here, we obtain this histogram there. Okay, and then we find we integrate from the left until we find 68% and 95%. And we should get 1 and we get a little bit more. We should get 4, we get a little bit more. So these are the corrections. And now we do this. We do this against the plot on the right. We do this again many times for many value of mu, and this is what we get: the green curve and the blue curve. So with again several months of work to get it correct. Every time there was a bug, a trivial one or subtle one, this was going crazy. That's very nice. But then now you see there is a small difference with respect to the expected. This is nice. And what was also very nice is that if we compare the same plot obtained with the classical analysis, so with the bin analysis, we see the shape is strikingly similar, meaning that the shape has nothing to do with the particularity of doing the bin analysis, but it is really due to the shape from the interference. And this plot was really crucial to convince our colleagues. There are 3,000 colleagues in Atlas, and we really have to convince them. It was crucial to commenter le zéro ou je prends comme qui perd un truc. Ouais, okay. So it was very crucial to use this to convince our colleagues that we knew what we are doing. So this has keep negative weight. Skip. And now we finish on the systematic uncertainties or epistemic uncertainties. So there are many things which can go wrong, from the details of the hadronization of the particles. So this is what happens at the core. This is what the really interesting stuff is at the core, but then it's only part of the protons which interact. So there are many things happening as well, and these are low energy. This is low energy QCD, which is really a pain to compute. So many things can go wrong, rely on simulation. This is interaction of the particles in the detector, where we have a lot of simulation to correct, but many things can go wrong. And this is read out by electronics, which can have the gain can change, and there can be noise, etc., etc. So there are many things, and so we have to take these into account. And so there are people who have spent a lot of time to evaluate all these effects. And then, as experimentalists, we are in the collaboration. We are given so-called up and down the data set. I mean, a data set where one specific source of uncertainties, which we call the nuisance parameter. Nuisance parameter can be, I don't know, the calibration of the jet, for example, is a bit off, so that people spend a lot of time to get it correct, but at the end there is always a remaining point. So the jets, if you measure 100 GeV, maybe it's 101, and the alpha measure the excursion with respect to the nominal. So we have 3 data sets, the nominal, and for each systematics we have the up and the down. Okay, and so compared to my formula, now this was the formula I had. Now I multiply this by a product of all the different systematics, which are supposed to be orthogonal, which is an important point. And then for each systematics, there is some distortion of the PDF. And this we parameterize again using an N classifier, which is going to classify the minus versus the plus, and then using this formula to do the interpolation, we are able to have a neural network which is able to predict formula which is able to predict the shape, the distortion of the shape for any value of the nuisance parameter, and then for any combination of nuisance parameter. And we do this. We do the demand construction again. A few months of work, and what you can see is that the dotted line is what happens with just statistics, and the green and the blue one is 2 different ways of computing the thing with systematics, and you see that it's very, 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 very close. Again, very reassuring that we see that there is nothing catastrophic happening in this case. And voilà, this is the final results, which was published just before at the end of last year. And so let me take you through this. The black one is what is observed now this time on data. Everything I've shown so far was on Monte Carlo. I've not shown many cross-check that Monte Carlo on data is well described, and we see that with the black, with this one, that the gain in sensitivity of this method is quite significant from here to there on the right, and the gain from here to there on the left. on the left. And also we can see now that we have, so it's 2 sigma, it's not quite 3 sigma, but 2.5 sigma maybe, evidence for interference with this new method, which we could not have with old method, which we had barely 1 sigma for evidence of the interference diagram. And voilà, my conclusion. So this was the one of the first neural simulation-based inference applied in particle physics. So there was many papers. This was the very first papers by Karl Kramer, was from 2015, I think. And so there was a lot of developments, but the first time this was really applied for real in an experiment. You see the reference, and what we find is this is really well suited in the case when there is nonlinear impact of the parameter of interest, which was really the case for this interference. But there are other cases where also there is interference, or other cases where we do want to measure details of the model. Thank you.
Thank you, David. Is there any question in the room? Yes.
Yes, thank you very much for this talk. I had a question about the calibration issues that you mentioned. Yes. About the neural network prediction for the likelihood ratio, and the fact that you eventually use the ensemble methods.
Yes.
I was interested to know more about the difficulties you had, because it seemed to me that what you were trying to do is close to what is known as conformal methods, yeah. Which are supposed to be well behaved because there are a lot of theoretical guarantees.
Yes.
And so why in practice it doesn't
work? There was
work?
practical method. Also, 2 students here, Hagansu and Zirui, they are using this method applying to a different data set, and they are working on this and their difficulties. One of the difficulties is that we need to do an LL log likelihood optimization after that. So we need our function to be derivable. And that's one problem, because this method, they introduce non-derivable points. So that was one issue which we have seen. But it's really work in progress. I mean, not for this analysis, but for the analysis which we are working. This is really work in progress. So we are interested to discuss with you if you have any practical advice on how to do.
I'm not a specialist of these techniques, but
because the ensemble does work, but it's very, very expensive.
Thank you.
Where do you talk? Like this?
So you can pass that around.
What is it? It's a microphone. Yeah, cool. I'm actually also part of the Atlas experiment.
Okay.
But maybe we can talk about it later. But there are some, according to my research, some issues with this that are more about
what is this?
This calibration or the that have to do with the parametric nature of neural networks. So you might have some, I guess you could just call it model biases because of this, which are going to be hard to deal with. But if you choose very appropriate neural networks, then you might not run into it, and maybe your ensemble kind of does that.
Yes.
Right?
Yes.
But you have 1,000. How many?
100? 5 times 1,000.
Neural networks?
No. 100 neural networks.
Ensemble.
The ensemble 100.
100, and you tried many different, and 100 seemed to be enough.
Yeah. Yes.
Yeah. I don't know.
We can discuss after that.
Yeah.
So exactly on this, you mentioned that in the ensembling of these 100 networks, that you use some kind of randomized data set? So are you doing some kind of cross-validation? Are you shuffling? What are you doing exactly?
Yes. The thing that for this channel, it's called the golden channel because there are a few events. With a few events, you can make a good measurement. So the ratio of Monte Carlo available to data is more than 1,000. More than 1,000 times more Monte Carlo than data. So we have a lot of events. We can do this kind of things. But for a more regular, more typical, I would say, analysis, this is also an issue that you don't have so many events to do this. That's another reason to have a better method to...
So the randomly sampled data sets were just randomly sampled events from a bigger data set, like the Asimov data set?
Exactly.
And these events are not the same across the different models? They are disjoint?
Yes, we take care of that, yes.
Thank you very much.
Hi, so thank you for your talk. So just a quick question. So how do you actually stop the training when you want to learn the likelihood ratio, and what kind of regularizer do you, because you mentioned the fact that you have to stop before the traditional flattening of the validation loss because you don't want to overfit?
No. We don't. No. That's the point. That what I really wanted to say is that. We do this. We are there. But thanks to the ensembling, we are not overfitting, and we don't have any problem. That's I think the whole strategy. Where do we stop? What neural network we use? What regularization method? Where do we stop? And what do we ensemble? I think we always have to ensemble at the end, probably, but not as much as that.
Okay, thanks.
Yeah, I was also wondering about this calibration curve you had on slide 16 and also 18 afterwards, because it's very impressive. I was working on calibration neural networks or something else, and I know how hard is it to get. So did you cherry pick your models, which put you on the good?
No, cherry pick. No, at the end,
for your ensemble, how do you really choose your ensemble?
No, there was two. One thing was to have a really large model, for sure. The other thing is that we have also, didn't mention that, we have also dropped. There was some features which were clearly not well, clearly causing problems, and by reducing the number of features also helped.
You really studied like the input.
Yeah,
yes. Everything, like, and also your parameters.
Yes.
Okay. Yeah, because I was just wondering if the ensemble is just a different set of hyperparameters, and you remove, let's say, like 20% of which doesn't give you the good result.
No, it's a random ensemble.
Okay,
Yes.
Perfect. Thanks.
Yes.
More questions? Okay, if not, we can thank David once more.
Thank you.